Now, Mr. Robert James Diaz from Mindanao State University, General Santos City, will present their study, A Deep Learning Approach for Accurate Prediction of Dust Accumulation Impact on Microsolar Voltage.
Today, I am going to present our thesis study entitled A Deep Learning Approach for Accurate Prediction of Dust Accumulation Impact on Microsolar Panel Voltage with the proponents Chris Dave Albios, Robert James Diaz, and Robertson Mantalaba. With our thesis Today, I am going to present our thesis study entitled A Deep Learning Approach for Accurate Prediction of Dust Accumulation Impact on Microsolar Panel Voltage with the proponents Chris Dave Albios, Robert James Diaz, and Robertson Mantalaba, with our thesis advisor, Engineer J.S. Villan. To begin with our introduction, we all know that the solar energy is increasing the vital component of global renewable energy solution, which is significantly influenced by environmental factors, particularly the dust accumulation on photovoltaic surfaces. Despite its potential, the efficiency of potential technology faces substantial reduction due to dust deposition, with some studies reporting efficiency losses as high as 50% in regions with intense dust level. Monitoring these adverse effects currently involves manual inspection and cleaning practices. These methods are rudimentary and it is labor intensive and subjective, falling short in providing accurate and consistent data for large-scale solar installation. The advent of machine learning, however, posits a promising alternative with demonstrative capability to accurately predict solar panel output based on dust distribution data. For the motivation of the study, it aims to utilize machine learning to develop an accurate and efficient solution for monitoring dust accumulation on solar panels, with the goals of optimizing renewable energy output and contributing to the advancement of machine learning in renewable energy research. In this study, we use CNN or convolutional neural network, and it is utilized to process and analyze high-resolution images to enable accurate prediction of solar panel based on the accumulation of dust. The ability of CNN is to recognize the pattern and extract pictures from images that allows to effectively capture the intricate the details of dust distribution on solar panels. For the objective of our study, we collect the dust deposition data or images. Next, apply machine learning for predictive modeling. Next, optimizing CNN for accurate prediction. And lastly, the model accuracy evaluation. For the scope and delimitation of our study focuses on examining the impact of dust accumulation on the voltage output of a micro solar panel and developing a machine learning model for voltage prediction based on the distribution of dust. Next, it includes the unpredictable patterns of dust deposition in natural environments, potential variation in dust composition, and the representation of diverse geographical location, which takes as the limitation of our study. For the methodology, the experimental setups begins with the collective limestone which was gathered in General Santos City, and it was crushed into finer pieces and sieved the fine process using the 106 micron mesh to collect the limestone dust. The experimental setup was composed of the light bulbs, which is 75 watts and 50 watts, and the dust is manually sieved above the microsolar panel and glass slide with varying duration to simulate a different dust condition. The dust images are collected using the digital trinocular microscope under 400 times magnification. Next, we have the image processing. First, we have the contrast stretching. This is to enhance the visibility of dust in the images and improves the differentiation between dust and non-dust pixel. Next is the thresholding or the Otsus thresholding. This is to convert images into a binary format, distinguishing dust particle from the background. And lastly, we have the erosion and dilation. This is used to further refine the binary images and achieve a clear or vivid representation of dust particles. For the model creation, the CNN has three parts. First, we have the input layer, the hidden or dense layer, and the output layer. The preprocessed images will be passed on the convolutional layers and max pooling layers for feature extraction. So there are two inputs in the input layer. First, the preprocessed image and the dust distribution. So the dropout will be applied in the dust layer to avoid the overfitting. For the model training and testing, the data is split into 80% for training and 20% for testing, with the testing data further divided equally for validation. The metrics include the root mean squared error, the mean absolute error, the R-squared score, and the mean absolute percentage error. These visualization plot were used for further assessment. For the results and analysis, as you can see in this table, this is the output voltages of different dust deposition from the dust images data. For the image pre-processing, so the original image, the figures above shows a sample of the original dust image. Next is the thresholded images. It shows the original image applied with Otsus thresholding and contrast stretching. Lastly, we have the pre-processed images. This shows the thresholded image applied with morphological operation, which is the dilation and erosion. For the creation of the model, we use the two activation function, which is the rectified linear unit and the hyperbolic tangent function. For the model evaluation, as you can see, we have gathered this result. For the metrics, we have 41.66%. The scattered plot represented the actual and predicted scatter plot, and this the visualization of the residual plot. For the CNN model, we use the graphical user interface to see how much percentage we have in the predicted voltages and for the dust distribution. To conclude our study, a comprehensive data was collected, capturing different dust accumulation levels and corresponding voltage output. The dataset formed as the foundation for data pre-processing and training a CNN model. Despite its minor processing challenges, the data's quality remained intact. The CNN model, with its multiple convolutional and max pooling layers that accurately predicted voltage under different dust scenarios. Evaluation metrics, including MAE and RMSE, demonstrated on high accuracy, while the R2 score was relatively low, and for the overall performance was notable based on the other metrics. For the recommendation, we have the following: the data collection in various environment, the extension of the extracted model application, incorporate additional input features, fine-tune the hyperparameters, and lastly, experiment with different network architecture. Thank you for listening.
Thank you so much, Mr. Diaz.